Good morning. I am Reggie, Associate Professor, Department of ECE. Today we are going to see about microwave filter design. On completion of microwave filter design, students will be able to define what is meant by filter, draw the filter characteristics. Design of microwave filter by insertion loss method. Some of the design trade-off for microwave filter synthesis using insertion loss method are: a binomial response is used when obtaining a minimum insertion loss. A Chebyshev response satisfies the requirement for soft cutoff. A linear phase filter design is used in cases where the attenuation rate can be sacrificed for better phase response. Characterization by power loss ratio. The insertion loss or the power loss ratio in the filter can be defined as PLR is equal to power available from the source by power delivered to the load. Pin by P load is equal to 1 by 1 minus gamma the whole square. The insertion loss in dB, IL is equal to 10 log PLR. Since gamma omega square is an even function of omega, we can express gamma as a polynomial of omega square. Gamma omega the whole square is equal to m of omega square divided by m omega square plus n omega square. So PLR is given by 1 by 1 minus m omega square by m omega square plus n omega square, where PLR is equal to 1 plus m omega square plus n omega square. Some practical filter response. Maximally flat. Such filter are known as binomial or Butterworth filter. For a low pass filter, power loss ratio is specified by LR equal to 1 plus k square omega by omega c the whole power 2n, where V is the order of the filter and omega c is the cutoff frequency. The power loss of the band edge is 1 plus k square. For omega is less than omega c, the attenuation increases monotonically the frequency. When omega is greater than omega c, PLR is equal to k square omega by omega c the whole power 2n. The insertion loss increases at the rate 20n by dk. Some practical filter response. EQ ripple. Such filter response is known as Chebyshev response. For a low pass filter, the loss ratio is given by PLR is equal to 1 plus k square Tn square omega by omega c, and for omega less than omega c, Tn is equal to omega by omega c will oscillate between plus or minus 1. The pass band response for ripple amplitude is 1 by k square. So omega is greater than omega c, the insertion loss increases at the rate 20n dB by dk, similar to binomial. However, insertion loss in Chebyshev filter is 2 power n by 4, greater than binomial response. You can see the practical filter response for maximally flat and EQ ripple for both Butterworth and Chebyshev filter for order n equal to 3. Some practical filter response. Linear phase. In some application, linear phase response is desirable in the passband. A linear phase response can be achieved with the following phase response. Phi of omega is equal to a omega 1 plus p omega by omega c the whole power 2n, where phi of omega is the phase of the voltage transfer function and p is constant. The group delay tau d is equal to d phi by d omega. Group delay is maximally flat response. Design steps in filter by insertion loss method. First you have to mention filter specification, then low pass prototype design, scaling and conversion, implementation. Maximally flat low pass filter. Consider the circuit with PLR equal to 1 by omega plus 4. When you find out the equivalent circuit, Z in is equal to j omega L into R into 1 minus j omega RC by 1 plus omega square R square C square. So PLR can be determined as gamma Z in plus 1 the whole square by 2 into Z in plus Z in star. The maximally flat low power filter prototype can be constructed with Z in plus Z in star. So using this value, we can compute j omega L plus R into 1 minus j omega RC by 1 plus omega square R square C square minus j omega L plus R into 1 plus j omega RC by 1 plus omega square R square C square, which is equal to 2R plus 1 plus omega square R square C square. Using this value, we can compute the value of Z in plus 1. Finally, we will get the value R by 1 plus omega square R square C square plus 1 the whole square plus omega L minus omega RC by 1 plus omega square R square C square the whole square. Maximally flat filter response can be compared by equating both real and imaginary part. You will get the value. Finally, you will get L equal to C equal to root 2. Ladder circuit for low pass prototype. Prototype beginning with shunt element, prototype beginning with series element. That is, we will connect the inductor in series as well as you will have no inductor with the shunt element. Once you find out the element, you can see there is a gradual increase. For practical filter, it is necessary to determine the order of filter. This is usually dedicated by the specification of the insertion loss at some frequency in the pass band. Impedance and frequency scaling. The prototype filter has RS is equal to 1, omega C equal to also maximally flat response, protocol has RL equal to 1. A source resistance of R0 can be obtained by multiplying all the impedance of the prototype design. The change of cutoff frequency from unity to omega C requires scaling of frequency dependent of filter which is accomplished by omega replaced by omega C. Note that the impedance scaling the scaled version of source and load resistance R0 and R0L. So design of Butterworth low pass filter. Consider a maximally flat filter having cutoff frequency 2 GHz and the filter have produced at least 15 attenuation, the source and load. Therefore, 1.5 into log 10 to the base 1 plus 2 whole power 2n. So G1 equal to 1, G2, G3 equal to 1. Finally, we can compute the value from different values for Butterworth and Chebyshev. Similarly, we are going to calculate the value of low pass filter prototype. PLR is equal to 1 plus k square Tn square into omega, where Tn of z equal to 0 for n equal to 0 and Tn for odd. PLR equal to 1 for n equal to even, 1 plus k square for n equal to odd. As the case for a different version of n, your value will be varied. So UQ-ripple low pass filter prototype has two elements. So this PLR can be computed 1 plus k square, that is 1 plus 1 by 4r 1 minus r square. So 4k square is 1 minus r square by 4r. So r is equal to 1 plus 2k square plus r minus 2k root of 1 plus k square. So you can determine the value of UQ-ripple low pass filter prototype. So we can find out determine the order of the filter. This is dedicated by the insertion laws. So low pass to high pass transformation. The low pass prototype filter design can be transformed to high pass, band pass as normally what we studied in the digital signal processing. After performing the impedance scaling, we can find out GK and CK. So low pass to band pass, band stop to band stop. That is omega is omega by omega 2 minus 1, omega by omega naught minus omega naught by omega. 1 by del into omega by omega naught minus omega naught by omega. So del is equal to omega 2 minus omega by omega naught. So similarly for band stop and stop band. There are different types of filter transformation: low pass, high pass, band stop. So now we study about the different type of filters and how they are using those filters. Thank you.